Hi everyone. In this video, we're going to look at a few more examples of volumes of revolution. So here we've been given a region which is enclosed by two curves. As always, I suggest starting off with a good sketch and make sure you're able to clearly identify the region being rotated. In this case, we're being asked to rotate around the line x equals -1, so we should include that in our sketch as well. And now we're ready to start slicing our solid to find the volume. We're going to use either horizontal or vertical rectangles. But notice the question does ask us specifically to use the disk washer method, and that implies the use of rectangles which are perpendicular to the rotational axis as discussed in the previous video. In this case, because we have a vertical rotation axis, that means we want to use horizontal rectangles with a width of dy to get disks or washers. And after all, if you visualize that rectangle rotating around your axis, you should see it forming a washer. And it's important that you're able to visualize that in order to correctly identify the dimensions of the washer. So pause here and think about it if necessary and really try to see that rotation in your mind. Knowing that our slices are going to form washers, we can use this formula for dv. And we know the radius big R of our washer is going to be the distance from the axis to the far end of the rectangle. Again, if you visualize the rotation, the formation of that washer, that's how you're going to know that that's going to be big R. So figuring out that distance would require the coordinates of these 2 points. Since it's a horizontal distance, we're going to need to subtract the x coordinate on the right minus the x coordinate on the left, right? Always look at the x coordinates for horizontal distances. So let's start with the coordinates of the point on the right. We do need to be mindful that we're calculating a dy integral, so our coordinates must be expressed in terms of y. We know y in terms of y is just y, and to get x in terms of y, we can rearrange the equation of this blue curve, which shows us that x is equal to root y. So that's what we're going to use as our x coordinates. That is x in terms of y. For the point on the left, we can still say y in terms of y is y. And by looking at the equation of this line, we can say x is -1. So subtracting these x coordinates of these 2 points gives us root y minus -1. And again, make sure you go right minus left to ensure a positive distance. And this simplifies to root y plus 1. So we've successfully found big R. Next, we need to find little r, which would be the distance from the axis to the close end of the rectangle. Again, visualize the formation of the washer to convince yourself of that. So that would require the coordinates of these 2 points. Once again, as a horizontal distance, this would be computed as x right minus x left. Remember that we still need the coordinates in terms of y, and for the y coordinate, that's just y. X in terms of y is found by rearranging the equation of the curve that the point lies on, and that tells us that x is y squared. That takes care of the coordinates of the point on the right, and we've actually already found the coordinates of the point on the left, so subtracting those 2 x coordinates gives us this formula for little r. And that, of course, simplifies to y squared plus 1. Going back to the formula for dv, we can now sub in what we found for big R and little r, so now we know the volume of all the slices. The last thing to do is add the slices together, and we know that's signified by taking the integral. But we need to know the integration limits, and for that we always look to our diagram. If we were to imagine slicing up the entire region, our first rectangle would be located at the bottom, which is y equals 0, and our last rectangle would be up at the intersection point, which appears to be at y equals 1, but as usual, we should confirm it by setting these curves equal to each other. It's just a bit of basic algebra from here to solve for the intersection points, so you can pause here and verify these details to check that they're at x equals 0 and 1. Keep in mind, though, that our integration limit should be a y value, not an x value, as you can see from the diagram. But to get that y value, we can just plug x into one of these functions. Either one of them will do. I'm going to use y equals x squared to get y values of 0 squared and 1 squared, and those simplify to 0 and 1 respectively. So that confirms that there's the intersection point at y equals 1, so we're prepared to use that as an integration limit. You could calculate this integral now by expanding everything out, but notice the question has only asked us to set up the integral. And whenever I say it that way, my expectation is that you tell me which integral would need to be calculated to find the volume, but there's no need to actually calculate it. So this is as far as we need to go with the question phrased as it is. And in general, when the question is phrased this way, I don't need you to go any further than this. Let's try this problem one more time, except this time we're going to use the cylindrical shell method. So that would imply that the rectangles are going to be parallel to the rotational axis. And in this case, that means vertical rectangles with a width of dx. Check that you're able to visualize that rectangle rotating around the axis to form a cylindrical shell. And when you can see that, we know that the corresponding formula for dv would be 2 pi r h dx. Now we just need to figure out the dimensions h and r. Pause and think about which distances in our diagram would represent those variables. I'm about to spoil it, so make sure you're ready to continue. If you were able to visualize the rotation, you can see that the height of the cylinder would be the same as the height of the rectangle. So for that, we're going to need the coordinates of these 2 points at the top and bottom. In this case, we're forming a dx integral, so we do want the coordinates to be in terms of x. So using the equation of this curve at the top, we find the coordinates there would be x comma root x. And similarly, the coordinates at the bottom would be x comma x squared. And with that, we're ready to compute this height, which would be the y-coordinate at the top minus the y-coordinate at the bottom, which is the same way we've always computed vertical distances. So with that, we've got the formula for h. But what about r? Well, once again, visualizing the rotation would reveal that the radius is the distance between the axis and the rectangle. Again, it's important that you're able to literally see the formation of that cylinder to convince yourself of that. So pause and think about it if you need to. Once you've identified this as the radius, we know that's going to require the coordinates of this point here. As a horizontal distance, r is going to be calculated as the difference of the x-coordinates on either side of these arrows. We know the x-coordinate on the right is just x, and on the left, the x-coordinate is going to be -1 according to the formula for that line. So that gives us x minus -1 as the formula for r. Of course, that can be simplified to x plus 1. So going back to our formula for dv, where I see r, I'm going to put x plus 1. And where I see h, I'm going to put root x minus x squared according to the work we did before. And with this, we know the volume of all the slices. So the last thing to do is add them all up by taking this integral. If you consider the position of the first and last rectangles, you'll see this intersection point is needed again, but we already found those coordinates when we used the washer method before, so let's not bother repeating those details. And since our diagram reveals that we're adding up rectangles from x equals 0 to x equals 1, we're going to use those as our integration limits. Since we were only asked to set up the integral, we can present this as our answer, and there's no need to calculate this to a value. Let's consider one more example. We've been given this region enclosed by 2 curves, and we want to rotate it around the y-axis. You'll notice this example didn't specify a method, so I've left it to you to decide which one to use. So let's talk about how to decide which method is a better choice. Students actually often ask the question of when should I use the disc washer method and when should I use cylindrical shells? But I think that's the wrong question to ask. The right question to ask is whether or not you'd rather use vertical or horizontal rectangles, and then whether or not you get discs, washers, or cylindrical shells will be decided for you. So pause the video and think about whether you'd rather slice this region using vertical or horizontal rectangles. And if you're ready to be spoiled, I'll give you my opinion on this. Technically, either way you do it can get the job done, but the superior choice in this example would be horizontal rectangles. And the reason for that is because there's this intersection point along the bottom of our region. That would cause a situation where the way you label the bottom end of a vertical rectangle would be different depending on where you put it. So you'd have to divide the region up and do two separate calculations of volume if you wanted to use vertical rectangles. But for horizontal rectangles, the ends would be labeled the same way no matter where you put it in this region. So that's what makes horizontal rectangles a superior choice. Now, the question tells us we're rotating around the y-axis, so are we going to get disks, washers, or cylindrical shells in this situation? Try to come up with an answer for yourself by visualizing the rotation of that rectangle. I'm about to spoil it, so make sure you're ready. Hopefully you can see that this rectangle is going to form a washer when it's rotated. And that's just a consequence of the fact that you chose horizontal rectangles in a situation where the rotational axis is vertical. The bottom line is that instead of asking whether you want to use disks, washers, or cylindrical shells, you should instead ask whether you want to use vertical or horizontal rectangles and let that decision influence your choice of method. Now that we've hopefully agreed on the washer method for this example, I want you to give a try to this one for yourself. If you do things correctly, you should come up with a final volume of 72/5 pi. I won't show all the details here, but if you have any trouble getting that answer, make sure to check in with me for help. But that's it for volumes of revolution, so I'll see you all next time.